Welcome to Counting by Weighing and Atomic Masses. So, when we want to count something that we have a lot of, so a large number of some object, it becomes impractical to count each item individually, so we count by weighing. So, let's say we have, say, a large number of jelly beans. Well, we don't want to have to sit there and count each individual jelly bean. If we have anything more than 100 or so, it's just way too cumbersome. And so what we instead do is we find out the mass of each jelly bean and find the mass of the whole collection of jelly beans and divide by the mass of each jelly bean. Now, we don't have to weigh each individual jelly bean, but we need to find an average mass of jelly beans. So we count out maybe 100 or so, weigh that, and find the average. So we take the mass of 100 of them, divide by 100, that's the mass of each jelly bean. So then we take the mass of our whole collection of jelly beans, whether it's 100 or 50 or 5 million, and divide by the mass of each jelly bean, the average mass. And as long as the average is reasonably close to the average that we're using, then we should have a pretty good estimate of how many jelly beans we have. And if we're estimating something like 5 million, and we're off by 35, well, who cares? We're up at 5 million, plus or minus a few doesn't really matter. So we can count by weighing. Well, we do the same thing with atoms, only with atoms we have way larger numbers. So, and molecules. So, if we want to count atoms in, a block of wood, well, we count it by weighing. So, we figure out what the average atomic mass is. Well, wood isn't just a single element, but let's say aluminum. Well, we know the mass of what a single aluminum atom should be. Well, we find out the mass of our block of aluminum, divide by the mass of each aluminum atom on average, and so we find the number of atoms of aluminum that we have. Now, the atomic mass that's listed on the periodic table is an average. It's a weighted average of the masses of atoms of that element, at least on Earth, the abundance of each isotope on Earth. And so something like carbon. Carbon has two stable isotopes. It's got carbon-12 and carbon-13. Now, carbon-12 has an atomic mass of exactly 12 AMU, because this is how an atomic mass unit is defined. It's the AMU, the atomic mass unit, is defined as 1/12 of the mass of a carbon-12 atom. And so carbon-12 has a mass of exactly 12 AMU, and of the carbon on Earth, 98.89% of them are carbon-12. Now, carbon-13 has an atomic mass of not 12 AMU, it has an atomic mass of 13 and change, I think it's 13.0034 AMU, and 1.11% of the carbon atoms on Earth are carbon-13. And so now we can find our average atomic mass, and we've weighted our masses. We've weighted our 12 AMU and our 13.0034 AMU by their relative abundances. So the relative abundance in fractional form of the carbon-12 is 0.9889, and the relative abundance of the carbon-13 is 0.0111. And when we solve this, we get 12.01 AMU. So that 12.01 is now our weighted average. That's our average atomic mass, and hereafter it's just going to be called atomic mass. For the most part, it will just be labeled atomic mass. So the atomic mass that's listed on the periodic table is an average. It's an average over all of the atoms. But note that no single carbon atom has a mass of 12.01 AMU. You can't find one. This is different from jelly beans, where with the jelly beans, you should be able to find some of the jelly beans have the average mass. Some of them have a mass higher, some of them have a mass lower. But with carbon, all of the atoms have either exactly 12 or exactly 13.0034 AMU. None of them have a mass of exactly 12.01 AMU. And that's because the masses that they can have are discrete, because the mass is determined by how many protons and neutrons there are in the atom. Well, those are quantized. You can't have a quarter or a 1% of a neutron. You have to have either 1 or 0 neutrons, or 1 or 0 protons, or some other number, but it's got to be in an integer value. And so the atomic mass is an average atomic mass. We can't ever go out and find some carbon atom that has a mass of 12.01 AMU. So suppose we have a sample of 12.01 grams of carbon, and we want to know how many atoms does it contain. And we also want to know how many atoms of each atomic mass does it contain. Well, we start out with 12.01 grams of carbon. We can use dimensional analysis to turn that into moles of carbon. Use dimensional analysis again to turn that into atoms of carbon. So we have 1 mole of carbon, or 6.022 times 10 to the 23 carbon atoms. And we know some fraction of them are carbon 12 and some fraction of them are carbon 13. So here I've replicated the calculation on the last slide to give us our number of moles. So now I've added in this ratio between moles of carbon 12 to moles of carbon, all forms, and moles of carbon 13 to moles of carbon, all form, and then change from moles of carbon 12 to atoms of carbon 12 and moles of carbon 13 to atoms of carbon 13. And we end up with 5.955 times 10 to the 23 carbon 12 atoms and 6.68 times 10 to the 21 carbon 13 atoms. So our sample contains those numbers of carbon atoms, or we have 1 mole of carbon atoms, so 6.022 times 10 to the 23 carbon atoms, and we have 5.955 times 10 to the 23 carbon 12 atoms and 6.68 times 10 to the 21 carbon 13 atoms. So that was counting by weighing and atomic masses.